So our goal here is expression for the average velocity of something when the velocities change. Like we're going to go with stick figure guy. If the stick figure guy at the start has a velocity of 0 meters every second, and as time goes on increases his or her velocity, we can say at the start, if we represent this using a motion map, the dots get further apart at any given point is increasing along some fixed x and y axis. Now, at some point in time, this person is moving with average velocity. We remember that average velocity is displacement divided by time, and it can also be thought at in terms of the word average. To find an average of something, you add up how many things you have and divide by the number of things. In this case, if we say that the thing starts with VO, with an initial velocity, and it would probably make more sense for me to draw the initial velocity over here along the velocity axis. If it starts with some initial velocity and ends with some velocity v, a time here, we can say that the average velocity is equal to the original velocity, VO, plus the final velocity, V, and since we're adding two velocities together and want to find the average, divide both of those things by 2. Now, this seems like kind of a ridiculous expression, but this will help us as time goes on to relate the starting velocity, VO, the ending velocity, V, as well as the average velocity, as long as the thing is accelerating at a constant rate. Meaning as long as the acceleration is not changing as time goes on, as long as it is accelerating at a constant rate, this expression allows us to link average velocity, original velocity, and final velocity together. So our ultimate goal here is to come up with a way to express the position of something that's moving in terms of other kinematics quantities like velocity, acceleration, and time. So if we start out with a situation where something is standing still. So for example, I'm going to draw a person because drawing stick figures is really the only thing that I excel at. A person who's standing still, we can say that their original position, XO, is the same throughout. It's not changing at all. So at any given time t, the position x is equal to XO for somebody who is just standing still. And that one kind of makes sense. So that's the first part of what's going to turn into a 3-part kind of expression. The first part is that for something that's standing still, the position anywhere is equal to the original position because it's not moving. That makes sense. What if we looked at a situation? Alright, what if we took a look at something that is moving, so rather than something that's standing still? Let's get our stick figure person, and let's give our stick figure person a velocity, have them kind of be moving along, in this case, the positive x-axis, it looks like. And it looks like this is an example of something moving with a constant velocity, since the position versus time graph is a linear function. So if we start just once again with the expression for a straight line, y equals mx plus b. In this case, y means the stuff that's on the y-axis. And the stuff that we have on our y-axis here, since the person's moving horizontally, on our y-axis of our graph, we have the position along an x-axis, which is kind of confusing, but just kind of keep in mind that we're just showing this guy moving in a straight line, straight horizontal line in this case. The position at any point in time is equal to the slope of the line, m, that's the next part of this expression, and we know that the slope of a position versus time graph is equal to how fast the thing is going, so we'll say v, and just to kind of keep things in check, we'll say how fast the thing is going at the start, the original velocity. times whatever thing is along the x-axis. In this case, along the x-axis, time is represented, plus the y-intercept of this particular graph. In this particular case, the y-intercept is 0, but let's say the graph looked like this, started here and went up. In either case, that's the original position, the xo, wherever the thing starts at, would be what the y-intercept of this graph represents. So we'll say that the y-intercept is the original position xo. So we can express this as saying that x is equal to xo, which is what we got from our first expression on the last slide, plus vo, and then just to keep things in one direction, vox times t. So that's 2 steps down, 1 step to go to get our full-fledged expression, because there also could be a situation where our stick figure man or stick figure woman is not only moving with a velocity, but is also accelerating. So that would mean that as time goes on, the velocity vectors are getting larger. So that would mean as time goes on, the velocity vectors are getting larger. And we kind of drew onto our graph, but the shape of this position versus time graph looks like a parabola. And we're not going to really do a full-fledged derivation of this equation. In your book, there's step-by-step, a whole bunch of steps of algebra of how to actually get to the end result. But we're just going to kind of look at what the position should be proportional to for this particular situation where something's accelerating. It looks like this graph's a parabola. And in math class, proportional. So y is proportional to x squared is the proportionality that defines a parabola. In this case, along our y-axis, we have the position along the straight line, straight horizontal line, and along the x-axis, we have time. So we have the expression that the position is proportional to the time squared at any point in time for something that's accelerating. And this is where I'm kind of going to be a little hand-wavy, but let's put the entire expression back together, where the position at any point in time is equal to the initial position plus, we said, vox times t, so the original velocity in the x direction times time, for if things are moving with a constant velocity, plus, and then just to make the units check out here, 1/2 at squared, and the a is going to be in the x direction. So what we have here is we have an all-encompassing, we call it a kinematics equation. Kinematics is the study of motion. We have an all-encompassing kinematics equation that defines the position along an x-axis in terms of the initial position, the initial velocity, time, and the acceleration along that axis. So I'll show you guys quickly how to do a sample problem with this, so you have some idea of where the numbers go into the equations, and then you guys can work on the 3 plug and chug sample problems for the homework. This is talking about a book being slid across the floor. It is initially moving at 5 meters per second. So I'm just going to list my knowns and unknowns. So we know that it's initially moving, so the original velocity is 5 meters per second. All right, and it slows down at a rate of 2 meters per second squared. So 2 meters per second squared, or 2 meters per second in the negative direction. That's information about our acceleration. So 2 meters per second squared, or 2 meters per second in 3 seconds. So that's information about the time, the 3 seconds. There's a question mark there. That should probably be a period, but that's okay. And the question wants to know how far does it go before stopping. Now, stopping is kind of a piece of hidden information. Stopping lets us know that at the very, very end, the final velocity is 0 meters per second because it comes to rest. Now, we want to find how far it goes, so we would like to know the position. Now, if we quick draw a picture to establish our coordinate system, we can say that this book, starts at the origin. and is going to move along the positive x-axis. So we can add that the original x position is 0 meters because it starts along the origin. It's initially moving at 5 meters per second, so 5 meters per second, and it slows down at a rate of -2 meters per second. So the acceleration is going the opposite direction of its motion. It's directed in the negative direction, and the acceleration is -2 meters per second squared. How far does it go before stopping? Okay, I'm quickly just going to go to the next page, so I have somewhere to write this stuff down here. Is that what I'm going to do? Okay. So we know we want to use our kinematics expression. The final position equals xo, the original position, plus vox, the original velocity along the x direction, times time, plus 1/2 ax times t squared, or the acceleration in the x direction, times t squared. Let's start plugging in some numbers. So we want to find x. xo is 0 meters. xo is 0 meters. Vox, so the original velocity is 5 meters per second, times a time of 3 seconds, plus, and I'm going to kind of move down here so I have some more room, 1/2 times the acceleration, which is -2 meters per second squared, times the time, which is 3 seconds, and that says square the entire thing. Now, 0 meters, we can kind of get rid of that, and I'm going to erase 0 meters, we can get rid of that because that's just 0. I'm going to kind of put a dotted line here so we can see what's going on. So x equals 5 times 3 is 15. Seconds cancels, seconds on the bottom cancels with seconds on the top, so the unit there is 15. Plus 1/2 times -2, that's -1 times 3 squared. First, let's take care of the squared because that's a little annoying. So 1/2 times -2 meters per second squared, times 9, because 3 squared is 9, square the number, square the unit, seconds squared, seconds on the top, cancel seconds on the bottom. So we have that x equals 15 meters, plus 1/2 times -2 is -1, -1 times 9 is -9, 9 meters, so our final position there is 15 meters minus 9 meters, so 6 meters in the positive direction. Put a box around that because that is our answer.